Hi, everyone. Today, we study Bayes' formula, one of the most powerful tools in probability, statistics, machine learning, data science in general, science in general. It's not only a formula, but it's a way of thinking, a paradigm. But first, a quick recap about the notions of conditional probability that we covered in the previous episodes. By definition, the conditional probability of event E given that some other event F occurs is this ratio. We can multiply both sides by P of F, thereby moving it to the left-hand side, and get what we may call the chain rule. The notion of conditional probability allows us to compute probabilities of any event by a trick called conditioning. Let's recall it. Suppose the sample space S is partitioned into two or more events. And for the illustration purposes, let's assume it's partitioned into two events, F1 and F2. We assume that these events are mutually exclusive. Then to compute the probability of any event E, such as this one, we can decompose E into these two parts. They're mutually exclusive, E intersection F1 and E intersection F2. And we sum their probabilities by the additivity axiom. To each of these two parts, we may apply chain rule. And this way we'll get probability of E conditioned on F1 times P of F1 plus probability of E conditioned on F2 times P of F2. This is the law of total probability for two events. Probability can be thought of as a measure of our belief in something happening, such as the event E. The notion of conditional probability allows us to update our measure of belief in the light of new evidence. The technical way to update probability in the light of new evidence is captured by Bayes' formula, which we're about to derive. But first, notice that conditional probability is not symmetric. It is not in general true that P of E given F is the same as P of F given E. To see this, consider the event E that someone has a brain, and F, the event that someone is a mathematician, in the left-hand side. If someone is a mathematician, what's the probability that he or she has a brain? All mathematicians have brains, in fact, very good ones, such as yours. So this probability is nearly 1. In the right-hand side, on the other hand, if someone has a brain, what is the probability that he or she is a mathematician? Not everyone who has brains are mathematicians. In fact, very few of us are mathematicians out there. So this probability is nearly 0. And that illustrates why you cannot trivially swap the order of conditioning. Bayes' formula provides us with a correct way to swap the order of conditioning. Let's discover it. What is the correct way to compute the right-hand side? By definition of conditional probability, it is the intersection of the two events, and the intersection is symmetric over P of that event, E. Now let's apply chain rule for the denominator. This is Bayes' formula. To make it more user-friendly, we can further compute P of E in terms of conditional probabilities using the law of total probability. We will look at the decomposition of S into just two events, F and F complement. So the probability of E, according to the law of total probability, is P of E given F P of F plus P of E given F complement P of F complement. Notice how Bayes' formula allows us to swap the conditioning. Our first example is about celiac disease. it affects 1% of the population. Suppose you are a doctor and a patient comes and asks, what is the probability that I have celiac? And you're too busy to do any tests. So you just respond, the probability that you have celiac is 1%. And you're generally right, unless you know something specific about that person. Now, suppose that person tests for celiac. She comes back to you with a positive result of the test. What is now the probability that she has celiac disease? Is there something extra that we should know? Something that's not given in this problem? Of course there is, the accuracy of the test. The accuracy is measured in two ways. The test can give a positive result for a healthy person, that's called false positive, and it also can give negative result for a sick person, and that's called false negative. Suppose that a blood test is false positive in 5% of the cases, and it is false negative in 10% of the cases. So false positive, again, means that the test gives a positive result where it shouldn't for a healthy person. And false negative means that the test gives a negative result where it shouldn't for a sick person. This problem is about the event that a randomly chosen person has celiac, and also about the event that the randomly chosen person is tested positive. Let's denote these events by C and plus. We would like to compute the probability that the person has celiac given that the person is tested positive. That's a conditional probability. We can use Bayes formula for that purpose. It's P of plus given C, P of C, over P of plus given C, P of C, plus P of plus given C complement, P of C complement. And now let's compute all these terms. What is P of plus given C if we know for sure that a person has celiac? What is the probability that the test is positive, that the test is correct? Well, the test is incorrect in 10% of the cases. So this probability is the complement of 0.1. Now, P of C, that's a probability that the randomly chosen person is sick, and that is 1%. The denominator starts the same. And then what is the probability that the test is positive given that the person is healthy? That is 5%. Now, the probability that someone is not sick with celiac is a complement of C, and that's 1 minus 0.01. If you put these numbers in the calculator, we get 0.18 or 18%. This is crazy. This is way too low. The test is pretty accurate. The probability of error is maybe 5%, maybe 10%. So we should trust the test if it is positive. And it is. So why is the probability she actually has celiac is so low? To resolve that paradox, think about how many people actually have celiac. A very tiny fraction. In fact, 99% of the people are healthy, and they take the test, and they come to the doctor. He rarely sees the actual person with the celiac disease because there are so few of them. And that's why the measure of belief for the doctor is actually so low, because the doctor thinks, oh, again, there is a person who is healthy come to my office with a false result. This is how Bayes' formula is non-trivial and can give us answers that are counterintuitive, but true. Quick remark, Bayes' formula generalizes for many events, not necessarily two. And that's because the law of total probability generalizes for many events, not necessarily two. Here's an example. Suppose a hiker went missing in the wilderness. The wilderness is divided into three regions, maybe mountains, desert, and a forest. The hiker is believed in one of these three regions with probabilities 0.5, 0.3, and 0.2. These regions have various probabilities of a successful search. Whenever anyone is lost in region 1, the search is successful in that region with probability 0.4. And for regions 2 and 3, the probabilities are 0.7 and 0.8. Imagine that you are leading the rescue team. Where would you send the team first? Maybe you will send the team to the region where the hiker went missing most likely, region 1. So assume you do that. You searched region 1 and have not found the hiker. What is now your probability that the hiker is still in region 1? In this problem, we're looking at these events. Ri, the hiker is in region I. I could be 1, 2, or 3. And also Ui, that the search in region I is unsuccessful. This problem is about conditional probability. Given that the search in region 1 was unsuccessful, what is the probability that the hiker is still in region 1? So we would like to compute the probability that the hiker is in region 1, given that the search in region 1 was unsuccessful. We will apply Bayes' formula for this purpose. Let me copy it over here. And in our situation, it's P of U1 given R1, P of R1 over P of U1. We will decompose P of U1 using the law of total probability. Here the sample space naturally splits into three events, that the hiker is in region 1, region 2, or region 3. The law of total probability for these three events gives the following: P of U1 given R1, P of R1, plus P of U1 given R2, probability R2, plus P of U1 given R3, P of R3. And let's compute these term by term. What is the probability that, given that the hiker is in region 1, the search there will be unsuccessful? The search will be successful with probability 0.4 and unsuccessful with the complement probability, 1 minus 0.4. What's the probability that the hiker is in region 1 without any conditioning? That's 0.5. And the denominator starts the same. What's the probability that, given that the hiker is in region 2, the search in region 1 is unsuccessful? 100%. They're looking in the wrong place. We assume that the hiker is here, so the search here will automatically be unsuccessful. So that probability is 1 times the probability of R2, the probability that the hiker is in region 2.3, plus, similarly, what's the probability that if the hiker is in region 3, the search in region 1 is unsuccessful? Again, always unsuccessful. They're looking in the wrong place. And so that probability happens to be 0.375. If you would like to practice, compute the probabilities that after the unsuccessful search in the first region, the hiker is in region 2. And you should get 0.375 if you apply Bayes' formula in the same way. Also compute the probability that upon unsuccessful search in region 1, the hiker is in region 3. That probability should be 0.2. And the sum of the probabilities should be 1. Just a sanity check, which they are. Before we did any search in any region, just from the general principles, we believed that the probabilities that the hiker is in region 1, 2, and 3 are these: 0.5, 0.3, and 0.2. These are the probabilities given to us here. These are called prior probabilities. Prior to any search, prior to any experience or evidence. The unsuccessful search in region 1 led us to update these probabilities. And the new probabilities, as we computed them here, are 0.375 for region 1, 0.375 for region 2, and 0.25 for region 3. Notice how our belief that the person is in region 1 decreased because we searched there and have not found the hiker. So these after-the-fact probabilities, the updated ones, are called the posterior probabilities. Now we can iterate. We can start with these new probabilities and send another team, let's say in region 1. Suppose you're adamant that the person must be missing in region 1 and you send another search there. And suppose, to your dismay, the team has not found the hiker there again. So another search in region 1 was unsuccessful. What are the new probabilities? Compute them. Do it yourself. Just do exactly what we did before, starting with these probabilities as priors. And then we update them again using Bayes' formula. What you should get is these new probabilities. The probability that the hiker is in region 1 gets updated to 0.26. Region 2 will be 0.45. And region 3 will be 0.29. Notice how our belief that the hiker is in region 1 got further decreased. The first search decreased its probability like this, and the second unsuccessful search decreased it to that. You can iterate it again and again. Now you may want to send the team to region 2, and you can do it yourself. What we just did is called the Bayesian model of learning, which allows us to update our beliefs about various things in our life based on our experience. And one last example. Sober drivers cause 75% of all traffic accidents, while drunk drivers cause only 25%. Sobriety seems to increase the odds of an accident by a factor of 3, which was ridiculous. So something is wrong here. What's wrong? Let's find out. This problem is about 3 events. Let event S be a randomly chosen driver sober. Event A be that a randomly chosen driver caused an accident. And D is that a randomly chosen driver is drunk. Let's interpret this statement probabilistically. Look at someone who has caused the accident. Assume that an accident happened. That person will be sober with probability 0.75. So it's a statement about conditional probability that the person is sober given that that person caused the accident. And that 0.75. However, the conclusion that sobriety increases the odds of accident is about the probability of making an accident if you are sober versus probability of making an accident when you're drunk. Jumping from this assumption to the conclusion, we're implicitly assuming that these probabilities are the same, but they're not the same. The paradox is based on the wrong identity. To correctly relate these two probabilities, we can use Bayes' formula. P of S given A times P of A over P of S. And we should compare this to P of A given D, which we'll again compute by Bayes' formula. To compare them, let's just divide one by the other. This way you will see which one is larger. So as we divide this by this, we can organize this as P of S over P of D times P of D over A over P of S over A. This is 0.75, the probability that an accident is caused by a sober driver. Therefore, this probability is 0.25, the probability that the accident is caused by a drunk driver. What about this one? But let's assume that every 1 in 10 drivers is drunk. It's a way of overkill, hopefully. But assume it's like 9 to 1. In that case, if we compute that, we will get 3. So even if we assume that 10% of all drivers are drunk, even then, being drunk increases the probability of an accident 3 times, not decreases, increases. So it is drinking, not sobriety, that increases the odds of an accident. And that resolves this paradox. Stay with me for the next episode.